How you guys doing this morning? Anybody awake out there? You guys all hear me okay?
Yep, we can hear you.
Great, thanks. Good morning. All right, so we are in the home stretch, you guys. We're in the last bit. We only have about 2.5 weeks left to our semester before we go into final exams. If you can believe it. So what's going to happen? We're going to finish up chapter 1 in the multivariable book. We have 1.3 and we're going to start 1.4 today. So make sure you've got your lecture examples for both of those. We'll be able to go through, I think, 1.3, and then, like I said, we'll start 1.4. 1.4 will finish on Wednesday, and then we'll start 1.5. And then after that, basically next week, so it looks like Monday next week we have off. That was one of the days that the provost gave us off. So we don't have class a week from today. That's the 12th of April. But we do have class 2 weeks from today, which is the 19th. So they switched those two. The 19th is Patriots Day, right? So they've kind of switched these off. So this week we'll do chapter 1.3, 1.4. We'll start 1.5. We'll see where we're at with that. We'll finish that up. Any other remaining questions that we have. We will have a quiz this week. It's probably going to be our last quiz. Maybe we can eke out another quiz next week. We'll see. Maybe not. But that'll be on the multivariable stuff this week. I'm looking at a calendar. That's why I keep turning away. Let's see, next week, like I said, we'll finish up chapter 1, and then we'll start reviewing for our final exam. In the next, by the end of this week, in the next few days, I'll start posting old final exams. I'm going to put that on I think it's on our last week's module. I'll post like old final exams to you guys if you wanted to start taking a look at old final exams to see what things were like and how you want to review for them. And we'll basically go through those on our remaining days after we finish up chapter 1.5. So kind of keep that in mind, some things that are coming along. We will have homeworks due. We'll have some homework due this week. I think 1.2, 1.3. Next week, I think, is 1.4, 1.5. We'll see how things go. Also, you guys, if you have any other outstanding homeworks you want to pass in, you can pass those in, in the next week or so. We can, I'll start collecting them. Remember, I'm moving forward with the current grading. So if you passed in old stuff, I'm not going to take a look at that until later. Okay, just to kind of keep that in mind. And anyway, phew, it's a lot of stuff coming up, right? We've got a lot of things that are happening. So, and just so you know, the final exam is cumulative for the whole semester, just to kind of keep your expectations straight on that. All right, so unless you guys have any questions, let's hold off questions for the homework on 1.2. If you guys have any, let's hold that off maybe until Wednesday, kind of give your brain a chance to kind of breathe from the exam, right? Hope you guys all had a good weekend after taking the exam. And then we'll talk about homeworks and stuff for 1.2, maybe 1.3 on Wednesday. Okay. All right. So with that said, let's go ahead and get started on chapter 1.3. Chapter 1.3, which is the dot product. And as part of the dot product, we're going to talk about other things that relate to the dot product. But do you remember when we were talking about vector arithmetic? We talked about what does it mean to have a vector? I can calculate the magnitude and direction of a vector. Like, how do I plot it? What's the geometry behind it? Also, we talked about things like scalar multiplication of a vector, right? So if I multiply a vector times just a plain old number, like times 3 or -1, what happens with that? What does that mean with the vector? And I said we're going to get to later if I multiply two vectors together, okay? So the dot product is one of those forms of vector multiplication, okay? So 1.3 is dot product. So the dot product in and of itself is a form of vector multiplication. But unlike scalar multiplication, right? So when we did scalar multiplication, there was a whole geometry behind it. We were just multiplying a number by each component in our vector. There's a whole geometry behind the dot product, and it's more complicated because we're dealing with two vectors, right? So you can think about this as, let's break this down into our input. So if I've got an input, I have two vectors, like V and W or V1 and V2, whatever they're called, but the output on the dot product is a scalar. Okay, so this is unusual. We're taking in two vectors and we're coming out with a scalar. Okay, unlike when we do in another chapter, I think chapter 1.5, we're going to do the cross product. Cross product is another form of vector multiplication. Okay, cross product, we take in two vectors, we get out a vector. The dot product, we take in two vectors and we get a scalar. Okay, so this is important to note, right? Set your expectations when you're looking at things. So without going into too much detail about where the dot product comes from, I just kind of want to show you a little bit. This thing, the dot product itself comes from the law of cosines. If you remember this from your high school trig, perhaps, the law of cosines, right? So let's just remember, I'm going to graph that out. So here's my x-axis, here's my y. Let's say, for example, I've got a vector, here's B, and I've got a vector, here's A, okay? And then basically, right, here's a line. I can draw a vector between these two. I'll call this C. If I look at the angle between A and B, right, A is a vector, B is a vector, theta is the angle between those two, okay? You can think about, here's the point here, I'm going to call this x1, y1. Here's a point x2, y2. So I'm starting at the origin, just as an example. We can do this with any vector. Remember, my vector B is the displacement from my starting point at the origin to my ending point at x2, y2. Okay, so remember how we calculate our displacement vector. So I've got these vectors here, A and B, they represent this. C is the displacement vector between x1, y1 and x2, y2. Okay, and theta is the angle between A and B. So my law of cosine says we're going to do this in terms of vectors, which means we've got magnitudes. So I've got the magnitude of C squared. This is magnitude of my vector C is going to equal to the magnitude of A squared, magnitude of B squared, minus 2AB cosine of theta, right? If you remember from your law of cosines, right, C squared equals A squared plus B squared, kind of looks like the Pythagorean theorem, but then we subtract out 2 times AB cosine of theta. But now that we're dealing with vectors, I can't just use C squared, I have to do the magnitude. It has to be the length of this vector here. Okay, but let's say I plugging in x1, y1, and x2, y2, right? So C is the displacement vector between x1, y1, and x2, y2. So you can imagine, right, what that is going to be, right? When I take the magnitude squared, that's going to be x2 minus x1 squared plus y2 minus y1 squared, square rooted, then squared, right? So it's just really the sum of those two. So I'm not going to go through, I'm not going to plug everything in and simplify it because I'm just trying to tell you where these things are coming from. But if I said I'm going to plug in and then simplify, right, what am I going to get? If I plug in x1, y1, x2, y2, and then I simplify, I'm going to get x1, x2 times x2 plus y1 times y2 is going to equal to the magnitude of A times the magnitude of B times the cosine of theta. Okay, there's a lot of simplification going on here, which I'm not showing you because it's not totally relevant to what we're trying to do. But this right here, right, these are two definitions for our dot product. We're going to write those down in just a minute. Okay, so when I say my dot product, they come from these two definitions here. These two are equal to each other. So I can say, let's codify that. So my dot product, okay, when we do the dot product, let's say, for example, I've got two vectors, V1, V and W dot product. So I'm going to say V, and then V could be X1, Y1. have the components x1, y1, and then W could have the components x2, y2, right? So these are the components of V. Actually, you know what? Let me just call this V1 and V sub x, V sub y, so we don't get it confused, because I think you might get it confused with Wx, Wy. You might get it confused with our coordinates, and that's going to be different. So I'll just call it V sub x, V sub y, W sub x, W sub y. Those are our components for V and W as our vectors. But my dot product, I'm going to say V dot W. It looks like a multiplication, but it's a little bit more like enunciated. It's got like a sort of a darker circle, equals, right? And what am I going to do? I'm going to take, right, my components Vx, Vy, Wx, Wy, and I'm going to multiply them together like we did here. So this is going to be Vx, Wx plus Vy, Wy. That's one definition. Okay. One of our definitions is we're going to multiply corresponding components together, and then we're going to sum those all up. By the way, this is all in R2, right? All real numbers in 2 dimensions, x and y. The math scales up to n dimensions, okay, but we're talking about like 2 and 3 dimensions here because it's easier to conceptualize. So this is definition number 1 for our dot product. Definition number 2, B dot W, is going to look like this. This one right here is going to be magnitude of V times the magnitude of W times the cosine of the angle between them. So I can use the dot product to help me figure out what's the angle between the 2 vectors. Okay, so that's going to become important. We're going to do that. Okay, so I'll write that down. I'm going to use the dot product to help me figure out what that angle is between those 2. So 2 definitions for dot product, they come from the law of cosines. Okay. Our 2 definitions are, I'm going to multiply corresponding components together for the 2 vectors that I'm taking the dot product of. I'm going to sum that up. Then my other definition is magnitude of one vector times the magnitude of the other times the cosine of the angle between them. Okay. So you guys finish writing that, and then we're going to go into the whole discussion of angles. You guys all set? All right, so let's remember, we're dealing with the cosine here. So dot product deals with the cosine. We're going to see when we do the cross product, that's going to be dealing with the sine of the angle. Okay, but this is dot product, we're dealing with the cosine of the angle. So let's remember, we're going to talk about the angles for a minute. So I'm going to go back to my trig, x and y, right? So my quadrants, okay, so I'm in quadrant 1. So this is quadrant 1, quadrant 2, say, for example, okay? Now in quadrant 1, I've got, of course, you know, x and y. This is in 2 dimensions, so my x and y. So in quadrant 1, x is positive, y is positive. Quadrant 2, x is negative, y is positive, okay? Now remember, when we're dealing with the unit circle, right, we're dealing with cosine of theta, sine of theta, okay? So our cosine of theta is going to track with the x coordinate, okay? So in quadrant 1, cosine of theta is positive, right? Because it tracks with our x coordinate. In quadrant 2, cosine of theta is negative. And that comes from our unit circle, right? We're tracking it around because our cosine, right, is going to be adjacent over hypotenuse. Hypotenuse is 1 on our unit circle. So adjacent is our x coordinate. So that's our cosine of theta. That's negative. It tracks with our x, okay? So remember that, okay? Now what happens, oh, and then here, right, at 90 degrees, our cosine of theta equals 0. Okay, at 90 degrees, or at, we'll call it, we have to be in radians, at pi over 2, okay? So at pi over 2, cosine of theta equals 0. In quadrant 1, we're dealing with angles that are acute. They're between 0 and 90. At quadrant 2, we're dealing with angles that are obtuse. They're between 90 and 180. Okay, so we've got 3 different types of angles that we're dealing with. Acute, right, and obtuse. Okay, and the dot product is going to tell us what's going on with these angles, right? I'm going to be able to figure out from the sign of the dot product if I have an acute, right, or obtuse angle. Okay. let's talk about that. So I'll call this how to use dot product to tell us about the angle between the two vectors. Right, the dot product is between two vectors, A and B, V and W, whatever, right? Whatever the vectors are called, okay? Those two vectors are separated by an angle, okay? Is that angle obtuse, right? Or obtuse, right? Or acute, okay? So let's think about it. So I'm gonna draw some pictures here. So I've got, let's call this, I'll do B, and here's A, okay? And then the angle between them, theta, like I'm trying to draw these a little bit to scale so we can see this. So theta is acute, okay? So our dot product is positive, right? Remember, right, we're in, acute angles are in the first quadrant, okay? So if my dot product is positive, that means that my angle is acute, okay? Let's draw it like, here's my A, here's my B, here's theta. The angle between them is a right angle, right? It's perpendicular. B, we would say B is perpendicular to A. So the dot product is actually a good test to see if two angles are perpendicular to each other. We need that. So that means that our dot product is equal to 0 radians, right? And why? That's because the cosine of pi over 2 is equal to 0. Okay, remember where you're at. You're basically along the y-axis, right? If I'm along the y-axis, my x is at 0. Okay, so our cosine, our dot product is related to cosine. Cosine of pi over 2 is equal to 0. So I can use the dot product to tell me if the two angles are perpendicular to each other. So this is a good test. So dot product test for what we call orthogonality. Orthogonal, perpendicular, normal, right angles, these are all synonymous to each other. We have a lot of different words to describe being at right angles, being at 90 degrees or pi over 2 radians apart. And that's because being perpendicular, having two vectors that are perpendicular is a really important concept. And we're going to get into that as we go along. Okay, so dot product equals 0 is a good test, right? These two vectors are perpendicular to each other. Let's draw out our last case. B, here's theta. So theta is an obtuse angle, right? So acute, right, means it's between, it's in the first quadrant, it's between 0 and pi over 2. Right angle means our theta equals pi over 2. Obtuse means the angles between pi over 2 and pi, 90 and 180 degrees. Okay, in this case, our dot product is negative. That's not a theta, that's a negative. I'll write this down, this is positive. Okay, so this is really important. So I can just take the dot product and I can know, generally speaking, that the two angles are acute, obtuse, or at right angles to each other. And we're going to talk about how we actually get the angle measure in a minute. Okay, so the dot product becomes a really good test for things. Okay, so before we go into some examples, I'm going to write down some properties of the dot product and then we'll roll through some examples of how we can use it. Okay. Especially when we talk about how do we calculate the angle. We're going to go through that. All right, so let's write down our properties. Of the dot product. Okay, our first property is A dot B equals B dot A. This is different than the cross product. Cross product order is important, but with the dot product we're talking about, we're just going to add things up. So it doesn't matter what order. A dot B is equal to B dot A. Okay, where A and B can be their vectors in any dimension. So this math scales up to however many dimensions we want. We're typically in this class going to be working with 2 and 3 dimensions. We can ask you to take the dot product of a 4, a 5th, or 11th dimension. vector, but it's gonna be hard to graph those. Okay, we don't need to worry about graphing the higher order ones. Okay, so A dot B plus C equals A dot B plus, oops, sorry, A dot C. That's an A dot C. Now, you can go either way on these things, and we write these out because there's an efficiency, right? So I'm only doing one multiplication and one addition. Here I'm doing two multiplications and one addition. So if I see something like this, like kind of like you can think about it like factoring out the A vector and then taking the dot product of the sum of the two vectors. So this is more efficient if you're writing a computer program to do the dot product, okay, than this one is here. We want to be thinking about efficiency because if our programs are efficient, then we can do a lot more computations, even though, processor speed is really fast. But the more efficient our programs are, the more we can do. All right, so where R is a scalar, SB, so let me write this all out and then we'll do this. RS, oops, sorry, times A dot B. And this is really just, let me get rid of that dot. That looks like it's a dot product, but it's really just a scalar multiplication. A dot B. Okay, so R and S are just scalars. Okay, so I'm going to multiply R and S, and then I'm going to multiply that product by the dot product of these things here. So this is more efficient than this one, right? So you can kind of think about, I'm going to factor out these scalars, and then I'm going to do the dot product, and then I'm going to multiply out those two scalars in the end. A dot A. You can certainly take the dot product of the vector itself, but that's really like saying I'm going to take the magnitude of A and I'm going to square it. Okay, so this is really just, remember our magnitude is taking each component of a vector, squaring it, summing it, square rooting it. So if I square our magnitude, I'm multiplying each I'm squaring each component, and I'm going to sum all those up. And I'm not taking the square root because that's defeated right there. Okay, A dot B equals AB cosine of theta. So we're going to manipulate this. This is the dot product. This is one of our definitions for the dot product, but we're going to use it to solve for our theta. Okay, so I'm going to want to solve for that. So remember, I can divide both sides by the magnitudes, right? So theta is going to equal to the inverse cosine of my dot product divided by the magnitude. Be careful when you're doing this on your calculator. Dot product is going to be a number. You always want to do the dot product out. We want to see the math too. I know probably a lot of your calculators have a dot product function on them, but make sure you're showing us the math on this first, because this is what we're testing you on right now. And careful on your calculators. If you do this, mine will do it like A dot B divided by A and then times B. Like if I just type it all in like this, you have to put little parentheses here to make sure that your calculator stays honest. Anyway, remember, we're always doing things in radians. Okay, but obviously you can get values in terms of degrees if you want to do that that reality check. But really, what we're doing in this class, everything is in radians, and this will give us theta is the angle between A and B, between the two vectors. Okay, so it's an important tool. It's going to tell us not only like is it acute, right, or obtuse, but it'll tell us what that angle measure is. Okay, so I'll let you guys finish writing those properties, and then I've got my lecture examples, and we're going to start rolling through some examples here. Okay. All right. So we've got the three vectors A, B, and C. Is the angle between each of them acute, right, or obtuse? What is the measure of the angle between them? Okay, so we're going to figure out, we're going to do the dot product first, and then we're going to find out what it is, and then we're going to actually go through and then figure out what those angle measures are. So we'll do them obviously in pairs. So first I'll go A dot B. So A is 1, 2, 3 dot B minus 2, minus 2, 2. Okay, so when I go to take the dot product, remember we're multiplying corresponding components together, and we're going to add that up. So this is going to be 1 times a minus 2 plus 2 times a minus 2 plus 3 times positive 2. So this is going to be minus 2 minus 4 plus 6. This is minus 6 plus 6 equals 0. We said that the dot product, when the dot product was equal to 0, that's right. So that means that A and B are perpendicular to each other because they're at right angles to each other. So let's do A and C. We'll check that out. So I'm going to go A, 1, 2, 3, dot, C, 0, 4, 1. So 1 times 0, see how I do x's, and then the y's, and then the z's. Okay, so this is going to be 0 plus 8 plus 3. So this is positive 11, positive, which means the angle between A and C is acute. We'll calculate these angle measures in just a minute. We're asked to do this part first, so I'm going to do that, and then I'm going to calculate B to C. Okay, so B is minus 2, 2, dot, 0, 4, 1. So minus 2 times 0 plus minus 2 times 4 plus 2 times 1. So this is 0 plus a minus 8 plus 2 is going to give me minus 6. So this is negative, which means that it's obtuse. Angle between B and C is obtuse. Okay. Now we're gonna prove it to ourselves. We're gonna actually calculate out what these angle measures are. So let's do let's see, angle between. So I'm gonna go A and B. So I'm gonna go, this is gonna be theta equals inverse cosine. Watch, actually, you know, we need to calculate the magnitudes first. Let me think about where I can do this. So I should have done that offline. Oh, let me scroll down just a little bit here. So I'm gonna go magnitude of A, because I need that for my inverse cosine. So it's gonna be 1 squared plus 2 squared plus 3 squared. So this is 1 plus 4 plus 9. So this is radical 14. Magnitude of B is equal to minus 2 squared plus a minus 2 squared plus a 2 squared. Be careful, make sure you've got parentheses on here if you're doing it on your calculator, because if I don't put the parentheses, my calculator will say minus 4 plus positive 4. I'm going to get a negative in the radical. If you get a negative in the radical on your magnitude, then your calculator has betrayed you. So make sure you go, this is going to be 4 plus 4 plus 4. This is equal to, I'm just going to leave this in a radical form. Okay, I'm not going to worry about simplifying. I'm just going to leave that because I'm just kind of calculating my cosines here. All right, and then magnitude of C. This is 0 squared plus 4 squared plus 1 squared. You don't have to do the 0 squared. I'm just showing you. So this is 0 plus 16 plus 1, which is radical 17. Okay, so now we have our magnitudes. I can use that in my angle calculation. So A and B. Right, we've got our dot product, which is 0 divided by the magnitude of A times the magnitude of B. Right, cosine, inverse cosine of 0, okay, is going to, if you do that on your calculator, it's going to give you 90 degrees if you do it in degrees, which we don't do degrees in this class, but just so you can convert in your mind, this is going to give you pi over 2 radians. Okay, be careful. My calculator actually doesn't give things to me in terms of pi. I have to be able to recognize what does that look like. It's like roughly 1.5 something, okay, because it's 3.14 divided by 2. Okay, so it's like roughly 1.5 something. So keep that in mind when you're looking at your calculator. All right, so the angle between A and B, angle between A and C is going to be theta equals inverse cosine of 11 divided by radical 14 times radical 17. So I plug this into my calculator, right? And I get out theta equals 0.77 radians. Okay, so remember, if pi over 2 is like 1.5 roughly, right? Less than, between 0 and 1.5 is going to give me an acute angle. So this is less than pi over 2. This is just from my reality check. B and C, right? Because this is the angle between. So theta equals inverse cosine of, I'm going to take my dot product, minus 6 all over the magnitude of B times the magnitude of C. I'm going to plug this all into my calculator. Make sure, like I said, you watch out for your order of operations. Make sure you have little mini parentheses here, so you can actually multiply radical 12 times radical 17, divide that product into minus 6, and then you're going to get, let's see, when I did B and C, I got 2.004 radians. Okay, which is greater than pi over 2. Okay, this is just a reality check here. Okay, which is what we thought it was going to be. We thought it was going to be obtuse. Okay, remember your 180 degrees, right, is minus pi, so it's minus 3.14. So we expect this to be between like 1.5 and 3, essentially. Okay, so keep that in mind. All right. You guys all have that there? Okay, so there, example 2, do you remember how we talked about in, I forget, it was chapter 1.1 or 1.2, we talked about another way to represent vectors was to use our unit basis vectors I, j, and k. So remember, I is equal to 1, 0, 0, j is equal to 0, 1, 0, and k is equal to 0, 0, 1. These are what we call our unit basis vectors. Okay, and they're used to help us represent essentially the x-axis, the y-axis, and the z-axis. Okay, so if I multiply 3 times I, that's like saying 3, 0, 0, minus 1 times j, that'd be 0, minus 1, 0, plus 2 times k, 0, 0, 2. I can add them all up and get a vector. So I can do this in one of two ways. I can multiply this out like it were, as though it were like just a I, j, and k. Will do that as well. But what I like to do to keep my math simple, I strip out the coefficients of I, j, and k, and I make this into, this is going to be 3 minus 1, 2. So I got the coefficients of I, j, and k, and I'm going to dot product that with I plus j plus, this is going to be times plus 0 times k. So this is 1, 1, 0. Okay, so let's just, I'm going to put a little note there. Plus 0 times k. Okay, let's write that. It's a 0, 0 times k. Okay, so that's, I'm going to do this dot product here. So this is like seeing 3 times 1 plus minus 1 times 1 plus 2 times 0 is going to equal 3 minus 1, oops, plus 0 is going to equal to 2. Okay, this is your most simple method. I'm also going to show you another method using I, j, and k. I can do it like a kind of like a binomial times a trinomial. Okay, so method 2, I'll write out longer method that's just as valid. I'm more likely personally to make a mistake on this one than I am on this one. I like to strip out the coefficients and just use them that way. But I'm going to teach you this just so you know. So I'm going to multiply. It's going to be 3i dot I plus minus j dot I plus 2k dot I. See how I did 3i times 1i minus j times 1i, 2k times 1i. Now I'm going to go through the other one. Plus 3i dot j minus j dot j plus 2k dot j. So I just distributed and I worked my way through. The thing about this is that you have to remember, let's write it in a different color. You have to remember that how i's, j's, and k's interact with each other. So I dot I is equal to 1. Something like I dot j is equal to 0. And the reason that is because we're dealing with, remember, I, j, and k represent our x, y, and z axis. Let's just draw this out. X, Y, Z. So here's Here's I. I've gone 1 unit. This is 1, 1. This is J, 1 unit. This is K. So they're all at 90 degrees to each other, right? Remember we said about the dot product, I dot J, this is 90 degrees, this is 90 degrees, this is 90 degrees. So I dot J is going to be equal to 0. That's like I'm dot producting two vectors that are at 90 degrees to each other, right? I dot I is going to be equal to 1. So this is going to go to 0. 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 So the only ones I'm worried about are here. Okay, so I'm dealing with 3 times 1 minus 1 times 1, right? J dot J is equal to 1. So 3 minus 1 is equal to 2. We got the same answer, which we should get the same answer. Okay, they're both equally valid. Whichever one you feel comfortable using, go for it. Whenever I see vectors like this, I usually strip the components and I turn them into just a simple vector instead of sums, like linear combinations of those. Both fine. So you know how to manipulate them both, and you'll recognize it when you see it. Okay. Any questions so far? Okay, I'm going to turn the page. All right. So we like to talk about geometry stuff. So we've got the triangle. We got a triangle with these vertices here. So I'm just going to do a quick sketch. Remember, nobody is going to grade your sketches, so you can do a quick sketch. 1, 2, 3, 4, 5. So I've got 1, 1, 2, 5, 2, 3, 4, 0. So I've got a triangle here. Okay, whoops, I didn't draw that very well. There. So I've got these triangles. This is my x-axis. This is my y. As long as I'm in 2 dimensions, maybe 3, I can graph these out, and then just kind of visualize it. So find the angles of the triangle with these particular vertices. Remember, if we were dealing with in just pre-calc, we would use our law of cosines to figure that out. Well, now what we can do is we've got the coordinates, so we can reduce these down to displacement vectors and then use our displacement vectors and the dot product to help us figure out these. So randomly, I'm going to just call, it doesn't matter how you want to do this, but pick one of them as like your initial and your terminal spots, and then you can, you know, decide on how you want to do that. For me, when I did this, I said A was going to be the vector between 1, 1 and 2, 5. So this is going to be my vector here, my displacement vector. So I'm going to go terminal minus initial. And it doesn't matter as long as you're consistent about, like this is my initial point. So that means this is going to be my initial point right there. Okay, so I'm going to line up my initial points between these two vectors here. So 2 minus 1 is equal to 1. 5 minus 1 is 4. So this is my vector A, my displacement vector A. I'm going to do the same thing for B. So B is going to end up, looks like I went B this way. I said 2, 5 minus 4. Yeah, okay, so I can do this one. So this will be B, and then I called this one C here. So I said B, right, was going to go from 2, I went this way. So 2, 5 minus 4, 0. So 2 minus 4 is minus 2, 5 minus 0. So this is my B. And then my C, right, is going to go from here to here. So I said this is going to be my terminal minus my initial. So it's going to be 4 minus 1, 0 minus 1. So this is my C. Okay, so I now have displacement vectors for A, B, and C. Okay, I can use the dot product to help me figure out what's the angle between these two. Okay, in order to do that, I need to figure out their magnitudes first, because I need to do the magnitudes on my theta equals inverse cosine of the dot product divided by their product of their magnitudes. So let's calculate their, I like to prefetch that out ahead of time. So magnitude of A, 1 squared plus 4 squared. That's going to be 1 plus 16. This is radical 17. Okay, my magnitude of B is going to be minus 2 squared plus 5 squared. So this is 25 plus 4. This is radical 29. my magnitude of C. This is 3 squared plus a minus 1 squared. So 9 plus 1 is equal to 10. Okay, so I now have my magnitudes for my 3 different vectors. So let's figure out, we'll call this theta 1. So I'll call this one, I'll write this in a different color. So theta, I'll call this one alpha, and then beta, just to keep it straight when I was doing the math. Okay, so my theta is the angle between A and C. Okay, which means, let's see, can you see that? Okay. Which means I need to take the dot product, right? So I'm going to go theta equals inverse cosine of A dot C divided by the magnitude of A, times the magnitude of C. So it's going to be inverse cosine of A dot C. So I'm going back to the components. So 1 times 3 plus 4 times a minus 1, that's my dot product, divided by my magnitude of A times my magnitude of C. Okay. So A dot C, so this is going to be 3 minus 4, so this is equal to minus 1 all over. So we expect this to be obtuse, right? So this is going to be 1.64 radians. Okay, we expect it to be obtuse because this is the dot product is negative. Okay, this sum right here, 3 minus 4 gives us a negative 1. I expect it to be obtuse. So remember, obtuse is like greater than 1.5, which is what we're dealing with here. Okay, so that's theta. Okay, now we're going to calculate the other one. So let's do alpha. That's the angle between A and B. Okay, so alpha, that's going to be alpha equals inverse cosine of A dot B all over magnitude of A times the magnitude of B. So inverse cosine of A dot B. So I'm going to go 1 times a minus 2 plus 4 times 5 all over magnitude of A, radical 17, magnitude of B, radical 29. That's a 9. Okay, so this is minus 2 plus 20. So this is positive. We expect that to be an acute angle. Okay, and what did I get out of here? I got 0.625 radians. Make sure you give us your unit on here so we don't, we don't think you got confused and give us degrees. Okay, so that we expect this to be acute. This is obtuse. Okay, so let's calculate beta, which is going to be the angle between C and B. Okay, C and B, so let's do that one. So beta equals inverse cosine of C dot B all over magnitude of C times the magnitude of B. Let's see what happens. All right, so inverse cosine C dot B. So I'm looking at my components for C, my components for B. So I'm going to go 3 times a minus 2 plus a minus 1 times 5 all over magnitude. Sorry, you can't see that. Magnitude of C, radical 10 times magnitude of B, radical 29. Okay. All right. So if I do this out, I get 0.868 radians. Okay. So let's just do a quick reality check, right? So theta plus alpha plus beta should equal to pi, right? That's 180 degrees, right? So 1.64, I'm rounding now, plus 0.625 plus 0.868 is like roughly equal to 3.133 radians. Okay. I mean, we rounded on these things here, which is why it's not exactly 3.14, so on and so forth. Okay, but it's close enough to pi that I feel like I'm in the right ballpark because I rounded. Okay, what do you guys think? You with me so far? Dot product is great. It's a very helpful tool. Okay. Whew. All right. So we're going to talk just for a minute about an application of the dot product. And you guys maybe have done this in physics class, and we're going to talk about sort of the math behind it. So the thing that we use the dot products for a lot is a thing called projections. So this is an application, one of the applications of the dot product. It's called projection. Okay, and how you've maybe seen it in physics is something like this. Right, we've got, let me draw it out this way. We've got a rod, right? And I've got a force acting on that rod. Okay, and the force is at some kind of an angle theta to the rod. Okay, so one of the things that happens is we want to break this down into the force on the rod and the force orthogonal or normal to the rod. So the force on the rod, and we would call this the force F sub n, which is our normal force, which means it's orthogonal to that. Okay, so a projection is I'm going to take this force and I'm going to project it onto the rod to find out basically our horizontal component of it. So let's write that down. So given a vector F, and I'm going to call this B, and a non-zero vector V, both of them, oops, in all real numbers nth dimension. So they have to be in the same dimension, obviously, because we're doing a vector math on them. They want them to be the same dimension. So I can say the projection of F onto V, which we write it like this, projection of F onto V. So V is like a subscript. Okay, I'm projecting F onto V, PROJ projection is going to equal to, we would write it like sometimes like this, okay, which is going to equal to my F that I'm projecting onto dot product with V all over V, whoops, sorry, V dot V. Remember, this is the magnitude squared of V times V. Okay, so this right here, let's break this down. This right here is a scalar. Remember, our dot product returns a scalar, and we're multiplying that by a vector. So what we get in the end is a scalar multiple of V, which is important because our projection, right, this green line here, I'm going to write this down here. This is our projection of F onto V. It's a scalar multiple of that. Right here, this force on the rod, okay, that's our, that could be just, it could be longer, it could be shorter, but when I project this force onto the rod, I'm going to get this scalar multiple of that vector going this way, okay? All right. So projections are really important. We use projections a lot in linear algebra, and we don't really go into it so much, but they're used a lot in like reflection. So if I have a vector coming in, it hits a surface and it bounces off, that's a reflection. We use projections a lot to do those reflection calculations. Okay, so projections are a pretty important concept for what when we try to do stuff with vectors. Okay, but let's do some examples here. So I'm on my lecture examples for chapter 1.3, example number 4. So I've got two vectors, F and V. We want to know what's the projection of F onto V. So we're just going to write this out. So the projection of F onto V goes like this. So I've got my F, that's 1, 2, 5, dot my V, minus 1, 0, 1, all over my V dot V, minus 1, 0, 1, dot times. Okay, so let's write this, I'll write that down in a different color. So that equals f dot v all over v dot v times v. So there's no dot here because this is a scalar, right? We're doing a scalar multiple of our v, right? So this is our v, this whole thing is a scalar. Okay, so let's go ahead and do it out. So the dot product, 1 times minus 1 plus 2 times 0 plus 5 times 1. See, I multiplied corresponding components together and I'm adding them up. I'll do that down here. So minus 1 times minus 1 plus 0 times 0 plus 1 times 1 times our v. So let's see what we get. This is going to be minus 1 plus 0 plus 5. So 5 minus 1 is going to be 4 all over. This is going to be 1 plus 0 plus 1 all over 2, which is going to equal 2 times minus 1, 0, 1, which I can distribute this as minus 2, 0, comma 2. Okay, so this is a scalar multiple of our v. It should line up, should be scalar multiple of our v. Now, what we often do with projections is we need to calculate this part right here. We need to calculate the orthogonal to our projection, f normal. That's the orthogonal to our projection. So let's draw this out. So here's our f, here's our v, here's our projection of f onto v, and then here's our orthogonal. I'll call this f sub n. That's the orthogonal. N means normal. So remember we have all these names for perpendicular. Orthogonal to projection of f onto v. Okay, I'm just going to use vector addition to help me figure that out, right? So how these add up is going to equal to f minus the projection, right? Because you can think about, I've got this plus this equals that, right, in terms of my vector math. Okay, so I can rearrange it to solve for that one. So that's going to, we know what these numbers are. So this is 1, 2, 5 minus, we just calculated the projection. So this is 1 minus a minus 2, that's 3. 2 minus 0, 5 minus 2. Okay. And that's your projection. And that's basically the end of chapter 1.3. Okay. Those are our dot products. Pretty neat stuff. Very helpful. Mostly, a lot of times, we use dot products as part of the projection. We also use dot products to figure out the angles, and we use dot product to tell us if two vectors are perpendicular to each other. Okay. All right. Once you guys have that, then we're going to start chapter 1.4. I don't know how far we'll get into it, but we're going to at least start it today, because there's a lot of stuff in 1.4. We're going to make sure we have time. Okay, so chapter 1.4 is called Lines, Planes, and Hyperplanes. Okay, it's the title, but we're basically talking about alternative representations for lines and planes. We always think about lines as being like, so in R2, we think about a line as being like y equals mx plus b, our straight line, right? So I've got my slope, I've got my y-intercept, I've got any particular point xy on my line, okay? And I want to be able to think about how I can write this out. So let me just draw a picture here. So I have a point, we'll call this x naught, y naught, and I have any particular point, x and y. This here, I'm going to draw it just a little bit above so you can see it. This here is our vector that's on the line. Okay. I have a vector that's normal to my line. I'll call this n. Okay, so let's write down what these things are. So I've got n is our normal vector to the line. So I would say n is perpendicular to my line. N is going to be perpendicular to my vector that's on the line. But we say vector that's parallel to line. This basically means our vector is on the line, but we call it parallel to the line because it can be, you know, scalar multiples of this line, but it's essentially parallel to this line. Okay, x naught, y naught is a particular point on the line. Like typically we're given that. You can think about that as like your y-intercept that tells you where is this vector anchoring in space. It's a particular point, and then x, y is a generic point on the line. That's like our x and y here. That means I can solve for x, y. Okay, so v is going to be a displacement vector between x naught, y naught, and x, y, or we could just be given v. You know, I could be given 2 points and then calculate v. I've got my, one of them is the initial point. We're going to talk about how we get our normal vector from these things in here. Okay, so now I can write my line as ax plus by plus c equals 0. Okay, where a and b are the components of our normal vector. It's what we call an implicit equation. We're going to talk about why that is. Implicit means we're implying our parameter. We're going to talk about parameters, vector representations using parameters of lines and planes in just a minute. But this is like our x and y equation, okay? But a and b are components to the vector that's normal, that's orthogonal to our line. Okay, let me write n is perpendicular to v, just so you know. Okay. I've got my lecture examples for 1.4. We're going to roll through these as much as we can as we go. Okay, so given this, so our first example, find an equation for a line in R2. So this is x, y, our 2 dimensions, which contains the point 1 minus 2. This is like our x naught, y naught, and is perpendicular to the vector 5, 2. So this is our normal vector. So as I'm reading these problems, right, I start to kind of think about how I'm going to plug these things in, okay? So what I need to do is I'm going to write down, and I didn't tell you that here. So let me actually tell you how I can come up with this equation from all this stuff right here. So let me go back to my notes. Sorry, I skipped a step. So I'm going to say a x minus x naught plus b y minus y naught equals 0. Okay, you're wondering where the c is coming from. Well, we're going to do that in just a minute. So I'm going to distribute all of this. I'm going to get ax minus ax naught plus by minus by naught equals 0. So a and b, by, plus, I'm going to put these together, minus ax naught minus by naught. This here is our c. It's a constant term. These are just numbers, right? It doesn't matter that they're negative. They could be negative, positive, whatever. Okay, it's just a constant term. A and b, remember, are the components for your normal vector. X naught, y naught, okay, are your specific point that anchors this line in space. Okay, so we're going to use this equation here to help us answer question number 1. So let's write, I'm going to rewrite this down over here. So a x minus x naught plus by minus y naught equals 0. Okay, where n equals ab. Okay, so we already have AB, we have x naught, y naught, so I'm just going to plug things into our equation. So I'm going to get 5 times x. Remember, x and y are our generic point. Let's see, minus 1 plus b2, y minus minus 3. And I can leave it like this. This is perfectly okay. This is an implicit equation for a line. Okay, or I'm going to distribute this out. So you can see 5x minus 5 plus 2y plus 6 equals 0. So this is going to look like 5x plus 2y plus 1 equals 0. or I can subtract the one on the other side. Both of these are totally fine. So this is what we call an implicit equation for a line. And you can do this in R2. When you get into higher dimensions, you must use the vector equation for a line, which I'm going to tell you about just right now. Okay, let you guys finish writing that, and then we'll go back to our notes. Okay, so let's talk about that vector equation. What does that mean? So remember that chart, that kind of graph that I did at the very beginning. I drew a line in space, right? I've got my x naught, y naught, and I've got some generic x, y as a point, and I remember I drew this vector that was parallel to the line. Okay, so now if I want to write out a vector equation, which is very helpful because it allows me to take it out of the coordinate grid, a lot of the coordinate space, and it allows me to actually write it in terms of vectors that are parallel to the line. So what I'm going to say is, I'm going to write, first let me write this out. So this is v1, v2, okay, and then we have the point x naught, y naught, okay, and then v is a vector parallel to the line. Okay, and let me tell you what things are first. T is our scalar. This is our parameter. I'm going to write that out first. This is going to help us create lines, points on the line, and parallel points. So my vector representation, my vector equation for the line goes like this. We call it x bar equals x naught bar plus t times v. Let me write out what those components are. So this is x, y, that's our generic. This is x equals x naught, y naught. Technically, this is a point and not a vector, but because x naught, this is a point, but it's a multi-component point. It's got x and y, so it tends to get written with a vector representation over the top, plus t times v1, v2. Okay, so this is how we write it in shorthand. This is what the components are. Okay, this is our vector equation for our line. I can use this, I can break this down into component pieces, which becomes very handy for manipulating lines and intersections. We're going to talk about that on Wednesday, and which is going to give me the individual parametric equations. So if I break this down into pieces right here, what am I going to get? I'm going to get x equals all just my x components, x naught plus t times v1. Now I'm going to do y naught plus t times v2. This is a parametric representation of our line. Okay, so this is what we call parametric equation. This is also a parametric equation too. It's all together, but we consider it as a vector representation. Breaking it into component pieces. Now I can take this, solve for t on each parametric equation, set equal to each other, because the t's are equal to each other. And then we're going to get what's called a symmetric equation. Your homework is going to ask you for all these pieces. So the symmetric equation, right, if I do this, I'm going to get x minus x naught divided by v1 equals y minus y naught divided by v2. And that's my symmetric equation, right? If I solve for t on each of these and I set those t's equal to each other. Okay. So unfortunately, we're out of time, but we will pick up with examples. Example 2 and the rest of it next time, but you guys should be good to go for doing homework 1.2, 1.3. Okay, we can talk about those homework problems either in office hours or on Wednesday's class. Okay, in Wednesday's class we'll keep cruising through 1.4. Lots of really good stuff in 1.4. Okay, all right, you guys, hey, have a great day, and I will see you on Wednesday. Okay, bye.
Thank you.
Thank you.
Thank you.